The reason I want my coordinate system like this is because I want my acceleration to be in the same direction as one of my coordinates. So I know my acceleration here is going to point to the center of the circle, so I want my r direction to be the same direction as the acceleration. So I'm going to draw my free body diagram. I have the Fg, I have the force of the normal, and my angle is going to look like this, where this is theta. So this is my z, my r is here, pointing to the center of the circle. And if this is theta, then I know that this is 90 minus theta, which means this is theta. These are perpendicular, so that means this is 90 minus theta, and therefore this is theta. So now I can calculate the sum of the forces. So the first thing I'll do is Fz. So in the z direction, I know that this is my z direction, and so I know that my forces are equal to 0, and I have my normal force here, and so I want the z component of it. So the z component is adjacent to the angle. So I'm going to have the force of the normal cosine theta. That's the z component of the normal, and then minus g, minus Fg, and that's equal to 0. So I know the force of the normal over, or times cosine, minus Fg equals 0. So the force of the normal times cosine theta equals Fg, and so the force of the normal is equal to, Fg is mg, so that's going to be mg over cosine theta. Now I want the sum of the forces in the r direction, so the sum of the forces in the r direction are equal to ma, and ma for circular motion is equal to mv squared over r. Okay, so now I have what are my forces in the r direction? The only force I have in the r direction is the r component of the normal force, and so the r component of the normal force is this part of the normal, and so that would be sine. So I have force of the normal sine theta is equal to mv squared over r. So I can plug in my force of the normal, so I'm going to have mg over cosine theta times sine theta is equal to mv squared over r. And so my masses cancel, and I have now g, and I have sine theta over cosine theta, and that's equal to tangent theta. So g tan theta is equal to mv squared over r. And I'm trying to solve for my angle here. That's the what banking angle is needed is the question. And so I know tan theta is equal to mv squared over r. So theta is equal to tan inverse of mv squared over r. So what values do I put in here? Well, I'm going to use the value that I calculated on part A, this 364 meters. But what am I going to put in for my velocity? And we allowed two different solutions. So we allowed you to use the 4 times bigger number or the 6.7 number, because we weren't explicit in part B about the safety and whether you had to increase the speed. So let's use, in this case, let's use the 6.7 number. So we have theta is equal to tan inverse. And I'm sorry here, I should have canceled my m's, so I'm going to take the m's out. And so I should just have v squared over r. So I'm going to put in 6.7 meters per second squared divided by 9.8. Okay, so what have I done here? I've left out my g also over here. So I have this g that I needed to divide by. So I need to add in my g here and my g here. So I've got 9.8 meters per second squared times r, which was 364 meters. So I calculate my theta to be 0.72 degrees. So that's going to be the angle that I need to bank at if I use the 6.7 meters per second for a velocity. If you decide to use instead for velocity the 26.7, so if v equals 26.7 meters per second, so that means you're accounting for the that you need 4 times bigger speed design in order to be safe, then my theta would be 11.3 degrees.